Alright, pre-video video. Yeah, so just giving you fair warning. So I did an hour video response to a video by icansciencethat, and he was doing the rolling, sliding something across a surface experiment. Let me just see if I can find an image there. So not rolling, but sliding instead, but it's the same mass, one going 1v, the other one going 2v. That's the established fact. You get it going 2v, it goes 4 times the distance. Clearly my argument is that friction is changing constantly. So the faster you're going, the less you weigh. If I put a scale under a road and I drive across it at different speeds, the scale will read a different weight depending on how fast I drive across it, because the fact is it's putting less pressure per inch on a surface the faster you go, because gravity is a time-dependent force. So if you go this much distance in a unit of time, or this much distance, it means all of the 9.8, let's say it's a second. If you're going slow, and this is the only distance you do, the full 9.8 is in this little tiny distance. You go this distance, well, now it's 9.8 over this entire length of distance, meaning the pressure, the weight, is much less per inch, meaning there's less force pushing the two surfaces together, and obviously creating a substantially different amount of friction, and therefore you're doing less work. You're exchanging less of your momentum with the surface the lighter you become. The faster you go, the lighter technically you are per inch on the surface. That's the absolute fact. That's the real subject. He never gets to it. So the video is a waste of time because I play it and he never talks about friction. And where he does, he basically says it's perfectly linear. It's the same every inch. And he actually says that the object goes half its speed at half the distance, when it doesn't. It goes half its speed 3/4 of the distance. In both cases, it goes half its speed 3/4 of the way down the track. That's an absolute Galilean proven fact. Alright, so anyway, so yeah, watch the video at your own discretion. And it was unfortunately a video I should have watched ahead of time to find out he wasn't going to address any of the issues that are the real subject. That there is no evidence there's 4 times the energy in the ground with the thing that goes twice as far. 4 times as far. No evidence there's twice the heat. 4 times the heat, sorry. There's twice the heat. Alright, till the next time, and such and so forth. On with the video. Alright, time for another draftphysics.com, debatephysics.com, also video presentation. So the icansciencethat guy has made a video. I don't know when it was made. I should look for that. Anyway, so I figure I'll respond. He's talking about friction, sliding friction. So probably should be about rolling friction, but whatever. Obviously I'm arguing that the friction changes with the speed at which you're traveling. That friction isn't a constant force. The faster you go, the less friction there is. The slower you go, the more friction there is. So that you don't proportionally move. You move more as you go faster. It's easier to move, and as you're going slower, it's harder to move. You lose more of your energy quickly. So we'll see if he presents any evidence to support anything he's going to say in terms of an experiment that demonstrates that friction isn't, as I just stated, because it is created by gravity, that it's time dependent. So it's how much time you spend on a surface will decide how much friction there is. Your weight decides. And your weight changes as you slide across a surface. You're weighing less per inch, is the simple argument. So let's see if we have enough volume here, and we'll see how it goes. Sorry for the added noise, but just life. Yeah. And such, real life, we want to say that way. Alright, so
I can science that.
Oh, that's way too low. So, no real choice but to increase the echo, I guess. I can't get this any higher. Okay.
Today we're going to talk a little bit about friction. I have a request from a viewer. The viewer has very politely requested that I look at this particular thought experiment and answer some questions that he has about that. And so that's what we're going to do today. Let's talk about the thought experiment. What we have is a block, a mass, that we are going to slide along a surface. Actually, in the original thought experiment, we were going to roll.
Yeah, well, that rolling makes it so much easier to do because you don't have to worry about what the surface is made out of, obviously. I mean, the difference between the wheels rolling on metal or wood isn't going to make any difference. But in sliding, obviously, depending on what you're sliding it on, makes a huge difference.
The mass
doesn't change the facts that you will have more friction the slower you're going, but the amounts will change depending on what the surface is.
But I would prefer to use sliding. I hope that's okay. Sliding is less complex than...
Oh, it's just the opposite. So, I don't know how he thinks sliding is less complex than a wheel rolling. Especially if the wheel isn't infinitesimally small and made out of the densest material on Earth. Wheels are pretty efficient.
Rolling because there's no rotation involved. We don't have to talk about whether there's any kind of fancy expressions that we need to do if objects are rotating. So let's just do the sliding. This is a thought experiment, but it is something that you could absolutely do at home. You could do what I like to call the dollar store physics. You can just get an object, a nice smooth surface.
So hopefully this is going to be the same mass, but moved at two different velocities. And obviously the one that's going to be twice the mass is going to go 4 times the distance. And the argument is it's not going to heat the surface with 4 times the energy. It's not going to happen. We also have the argument, if he's changing the masses, that the springs will be putting different amounts of energy into the objects because of the way springs function. But we'll see what he's going to do. See if they're the same mass.
Some kind of hard object. Like, don't use rubber or anything too sticky. Probably like a metal thing. And then slide it along the floor. And then
again, it's not the ideal way to do the experiment, but it won't change the results substantially.
And your goal would be to measure what is the position of the object over time as it slides and as it eventually comes to rest. So you'll slide the object, and then you just need to measure those positions over time. And I think a really good way to do that might be to just film it. If you lay out marks along the sliding surface.
So all of this has nothing to do with getting to the real question. You know that the spring puts the momentum into the objects. The argument is, did it put kinetic energy into the objects? And the only way you can know that is you have to collect the energy in the ground. You have to collect the heat created. So if you're not going to use a joule tank, or you're not going to use some other mechanism to actually see what the impact energy is, and you're just going to say, well, it went 4 times the distance, therefore it was 4 times the energy, that just isn't true, because the friction wasn't constant through the whole path it traveled. And you can tell by where it goes half the speed. That'll be the big giveaway.
Of distance marks along there, or put a measuring tape down along the sliding surface, and then simply film the thing sliding. You should then be able to go back through the recorded video.
This is the part where, whatever. This is a guy who's spent his life being a teacher, and so this is what he's going to do. This is how to ignore all the important variables and just do a superficial experiment. Yeah, well, that's really not good science in my opinion. Educators aren't really scientists. They're just reading out of a book,
Video frame by frame, and mark down the position of the sliding object at every time interval. And then you can create a graph of the position of the object as it was sliding, and from there, work out the velocities of the object.
So in the case of, you could just change this scenario and say if you're sliding it on ice, a hockey puck might go, 100 yards. So you're making a mess out of what this experiment's supposed to do. And I think the reason why somebody brought it up, so he's sort of just evading the reason why it was brought up, which is to illustrate the fact that friction's not a constant force, that it's velocity dependent. The faster you go, the less friction. The slower you go, the more friction.
At different time
inch of distance.
Intervals, and you can work out the accelerations that you were seeing over those different time intervals. And I think it would be very, very easy to do, and might be kind of fun if anyone's interested.
Why would it be fun? Yeah, that's the part that I'm missing. That watching experiments is fun. Doing experiments is a pain in the ass.
So let's take on your thought experiment. We're only going to do it in digital form. We're not going to do it in meat space today, but this...
So he's not going to test anything. He's just going to give us this textbook version of it for which there's no evidence. So a completely unexperimentally verified output will be given as this is the truth, when he'll have nothing to prove it with.
This is what you've put forth. The second mass is the same mass as the first.
Good.
So I have my yellow mass and my blue mass, and I'm going to say, let's make this easy, 1 kilogram each. Alrighty. And, maybe I'm using a spring to shoot them, or you could just flick it. Like if you're just doing this on your own, you don't need them to be a particular velocity in order to...
Oh, I think you do need them to be a particular velocity if you're going to do anything reasonable. So that doesn't even make sense. How can you compare it if you didn't do any... how can you do a fair comparison if you don't have explicit velocities? I mean, so that's just silly, frankly. The experiment isn't going to show enough the way he's doing it, and to flick them means the experiment is absolutely useless. There's just nothing, no conclusion you could draw about anything. Except flicking it harder made it go further. Yeah, duh.
And take these measurements, you could do any velocity you want. And so just flicking the thing could give you data that's just fine.
No, it's useless. Insanely useless.
But you have specified that the first one is going 1v and the second is going 2v. So let's give those some units. We'll call them 1 meter per second and 2 meters per second. So we're going to launch these guys.
It's unfortunate. He's going to waste 31 minutes. My video on this subject is, I think, 12 minutes. So you would think he could just draw it and explain how it works in 12 minutes and tell us what his theory is, okay, about where it's going half its velocity. Because that's the trap here, right? As soon as he has this thing go 4 times the distance, and we have one other version where it's going 1 distance at 1 velocity, we're going to know, okay, that 3/4 of the way down the track, it's going half its speed.
We launched the blue one at 1 meter per second. We launched the yellow one at 2 meters per second. And what's going to happen? Boom! We'll see that because the yellow one is going faster, it goes farther. And there's no controversy there. We're all on board there. And also, it took longer to stop. I think.
It's just 2 units of time. So longer is way vague because it's really important to the subject. Because it's just like falling in gravity. You can fall 4 times the distance and you're only in the gravity 2 units of time. You're going 4 times the distance, but you're only in the gravity, again, 2 units of time. It's a really important fact.
You'll notice that it starts off faster. It's going to go for longer, and it's going to go farther. Okay, sweet. That's our setup. You have mentioned the first one travels 1 distance, the second travels 4 distance. And I would agree with conventional physics suggests that's probably going to be a good approximation of how far they go. If you give it twice the speed at launch, it actually goes 4 times the distance when sliding. And we did see that they traveled for different amounts of time.
So it's not just different amounts, it's an explicit important amount. It's not 3 seconds or 4 seconds, it's just 2.
So what are those times? We're going to need that. If the yellow one starts off with twice the speed, right? Starts off with twice the speed of the blue, it will take twice as long to come to a stop. If we're expecting constant deceleration, constant acceleration here.
All right, so it's not anywhere near constant because of the fact that the faster you're going, the less energy you're losing to friction.
It will take twice as long to lose 2 meters per second as it takes.
No, because that's why you're going half your speed 3/4 of the way down the track. Is because you didn't lose speed proportional to the distance. You lost your speed not proportional to the distance, indicating the friction wasn't constant.
So it was 1 meters per second. So in our thought experiment, the blue object takes 2 seconds to come to rest, and the yellow object takes 4 seconds to come to rest. All right, so here comes the question. That's the setup. Here's the question. You would need to explain how it has 4 times the energy in this circumstance when the first travels 1 distance, the second travels 4 distance. Okay, the key word here, the vocabulary word is energy. I want 4 times the energy. So in order to quantify the energy, I need to know what exactly the energy is so that I can put a number to it. We need some definitions. So I'm going...
So obviously the way the question's asked, it's you go, well, went 4 times the distance. That's what the book says is 4 times the energy. 4 times the distance, 4 times the energy. But that's only if you can rationally defend the fact that the gravitational friction is constant. If the gravitational friction isn't constant, then you can't make the excuse that there's 4 times the energy in the ground. That's what he has to demonstrate. Do you believe that what should have been asked is, do you believe the ground is 4 times hotter under the thing going twice as fast? Is the ground 4 times hotter? That's the question we need this physicist to answer. If he says yes, then he doesn't believe you can slide across thin ice. If he says no, then he has to explain why he believes in kinetic energy when you can't collect the energy it creates, when it's not conserved at all. So then, unfortunately, I'm very grateful somebody provoked him into responding, but I guess the point would be is to have him to actually respond to my actual arguments would be better.
To use contemporary physics definitions in the context of a high school physics classroom. That's what I want to... That's about the level of discussion I think is appropriate right now.
Whatever. It's not appropriate to any of the people involved that are viewing your video now that are from my audience. We're not interested in the version you do for 7-year-olds. We're interested in the truth. Okay, what actually happens, and an explanation for what actually happens. Not a bunch of blah, 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 blah. Unevidenced blah, 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 blah.
So if you're, just starting in high school and you're taking your first physics class, they would need to define what is energy so that we can use that word and everyone knows what...
Look, the point is yes, you've stolen the word, okay, for the word motion. You're saying motion equals mv squared. And clearly the alternative use of the word energy would be for just saying what anything moving that has momentum would be called energy. You're saying that's not technically energy. So momentum isn't technically energy, because you're saying it's a narrow definition for when we can use this word energy. We can't use it for any motion. We can only use it for motion squared. I think that's just cheating the argument, frankly. So why don't you just say kinetic energy, okay? And we'll say momentum and try to just use those two terms and just leave energy out of it.
That word is supposed to mean. So I'm going to suggest a website for that instead of a literal textbook. Let's go to a website.
So again, who wants this shit, right? We all don't need you to do this crap, okay? This really isn't the 5th grade. Oh, brother.
Site targeted at that level, and I found one that I think works called joules. So let's go and look at that. Okay, here we are at byjules.com, and the definition is given for energy. Energy is the ability to do work. Okay, this leaves us with an obvious problem, which is, what is work? I can't define energy in terms of work unless I know what work is.
Right, and you're not going to have a reasonable definition of work, so there's just no point. Work's going to be, in one context, the energy we like. Heat is waste. But clearly, heating something is work. You'd have to do work to heat things. If I'm going to try to start a fire and I'm going to try to get something hot, I'm going to have to do a lot of work to make the thing hot. Okay, so obviously even making heat is doing work to make heat. So again, this is just kind of mush. The argument should just start with the idea that whatever we're going to say energy is, it has to be conserved, and you can't destroy it, and you can't make it. You can only transfer it.
So let's go and look up work. Okay, here we are. Work is the product of the component of the force in the direction of the displacement and the magnitude of this displacement. Kind of a mouthful. Here's the mathematical expression, right?
So kind of a pile of crap in this case, right? Because we know all the energy didn't do that. So all the energy was lost to the ground. None of that motion is really in the same direction that the thing was moving. It's going in all kinds of tangential directions. So that definition doesn't mean anything. It's not very useful. But bowling pins don't even go in the direction of the bowling ball. I mean, they hit off the side. They hit in all kinds of angles. So the substance of the energy probably doesn't even go in the direction of the ball. So the whole thing is just kind of a bullshit definition, because we know if we're going to conserve kinetic energy, we're going to have to find the energy going in all those tangential directions. The work will never equal the kinetic energy in. So we know that the kinetic energy definition saying energy is the ability to do work, we know it doesn't do any work in a ballistic pendulum, and we know it doesn't do any work in a rocket engine. So in those two substantially simple cases, kinetic energy will not be found doing anything called work, doing any motion in the same direction. The spaceship only goes based on the equal and opposite reaction to the momentum, and the ballistic pendulum does the same thing in the sense the only energy that gets collected as linear motion in the ballistic pendulum is the momentum, none of the kinetic energy. None of the kinetic energy over the momentum. So we know in those two cases it's not anywhere near conserved. So it's just, this is a bullshit definition. This is just playing with vocabulary, and it's really a waste of time because it really doesn't get to the subject, which is, can you prove there's 4 times the energy in the object moving twice as fast? Can you show us it doing 4 times the actual work? Not 4 times the sliding across ice. No, 4 times of real work, which isn't going to be just about distance. It's going to be how much heat can it create?
Here, that part, we'll look at that part. That's the mathematical expression. What are we saying? We're saying an object is moving over some distance, so that'll be d. I think we don't need a definition for distance. I think we're all on the same board, same place there. And then we want to take the amount of displacement, right? That's the distance the object moved, and multiply, product means multiply, by the component of the force in the direction of the displacement. So that's this. This is, you're pushing on an object with some force, And whatever amount of that force is pointing in the same direction that the object is moving, that's...
So we know none of the force is left. So this is not an appropriate equation to even be using, because there's no force left. You're taking it all out of the object. When the experiment's completed, there's no... This isn't an example of, what happened. We're taking the energy out of an object by sliding it. We're not putting energy in. We're taking it out. The whole point of... You could just measure the pressure at takeoff if you want to say what's the value of the spring's pressure. And I'd argue it's going to get the same answer. All you're going to do is collect the momentum. But regardless, the point is the whole point of sliding it is to take the energy out of it and then have some measurement of the energy you took out of it. And how do you figure that out? And I'm arguing you figure it out one way by realizing if it's going half its speed 3/4 of the way down the track, it obviously didn't lose energy proportionally. Obviously.
The amount of force that we put into this equation. So that's what that cosine theta there is. So, but in our example, that's going to simplify. But if we're going to we're going to define work in terms of this thing called force, we need a definition for force. So here's force. Force is the push or pull on an object with mass causes it to change its velocity. Okay, so what are we going to need? We're going to need a push or a pull of some kind, and it has to be on something with...
So again, we're not measuring the spring. We're already saying the spring's twice as compressed. It's going to create, hopefully, twice the velocity. Obviously, there's a doubt about whether it actually will be twice the velocity, but anyway. And the only thing we want to know is the force on the ground, the force that goes into the ground. That's what we want to collect, and that's what we want to claim, make a claim about how much there is. My prediction is there's only twice the heat, the force in the ground. Your prediction is there's 4 times. And the question is, why in 350 years have you never done the experiment to find out how hot the ground is?
Mass, and that mass has to change its velocity. What we're going to do then is we're going to say that if we observe a mass, and that mass is changing its velocity, then we are observing a force, because that's the definition of a force that we've got here. The definition of a force, and there's a few of these, they don't all line up, but let's use this one for our discussions. The definition of a force says that if a mass is changing its velocity, we are seeing a force. We're going to need to know exactly how much force. So in order to quantify that, to put a number to it, we will use this equation, F equals ma.
Oh, bullshit. It has nothing to do with the experiment and demonstrating that it's 4 times the energy. So again, it's useless.
And where do we get that equation from? That is Newton's second law. However, it should be stated that is not how Newton wrote his second law.
Oh, there you go. Right. It has nothing to do with Newton. That's right. Because Newton didn't say per second, and Newton didn't say let's square the seconds for no good reason. None of that's Newton's physics. Newton believed in momentum. The first law, second law, third law, all relates to momentum. Kinetic energy doesn't obey the third law. It doesn't create equal and opposite reactions whenever you transfer the energy from different masses. So whether you transfer it from a light thing to a heavy thing or from a heavy thing to a light thing, you won't conserve the kinetic energy. There won't be the same. The gun and the bullet is a perfect example in the sense that the bullet has 2,000 joules, the gun recoil is 2 joules. Obviously, in kinetic energy. In momentum, they both have 2. But in kinetic energy, they have this extreme difference. And clearly, that's not obeying the rule that there's supposed to be an equal and opposite amount of energy.
Originally, this is the contemporary writing of Newton's second law. It has the same meaning that Newton originally did.
No, it doesn't. So that's just a lie. It doesn't at all.
Discussed, but this is using our nomenclature, the nomenclature that we're going through right now. So this is essentially the translation of Newton's original text.
Yeah, it's not a translation. As stated, it's a perversion. They're just perverting Newton's physics into Leibniz's physics Newton wasn't a Leibnizian.
Into modern contemporary physics classroom.
Modern bullshit. Lying, frankly. Lying about what Newton believed.
Okay, so we're going to need to know, if we're going to do this, force, we need one more definition. I'm going to assume we know what mass is. We've been using mass already. You gave me some masses, so I'm going to consider that one done. Acceleration. We're going to need a definition of acceleration. So here we are. Definition of acceleration.
So acceleration is useless because all we're really going to measure here is deceleration, frankly, because we've already set what the velocity is. There's no acceleration in the experiment that's relevant. We're saying it's going twice the velocity. Now we count. The other one's going one velocity. Now we count. There's no acceleration.
Acceleration, the rate of change of velocity with respect to time. All that means...
Right, and so there's the giveaway, is that now it's with respect to time, but later it's going to be converted into with respect to distance, because they're going to average the acceleration and turn 9.8 into 4.9, okay, and then claim there's 4 units of 4.9. Well, of course there are, but you didn't get gravity in those 4 units. You only got gravity in the 2 units of time. You didn't get gravity in 4 units of distance. Newton didn't write 9.8 meters per meter. He didn't write it as distance. You don't get gravity in units of distance. You get gravity in units of time.
Is you take however much...
Look, the simple argument is 1 unit of gravity, 1 unit of time for gravity to push something is an amount of weight. 2 units of time is twice the weight. So you can just understand that it can't be 4 times the weight. It's only twice the weight. It's only 2 units of the force hitting the object, pushing it into the ground. There's only that much pushing, twice the pushing. There's not 4 times the force anywhere. There's only 2 units.
Your velocity changed, divide by how long it took to make that change, and that is the quantity we are defining to be acceleration.
I don't know. This is going to get insanely boring, right? Because he's not going to show us anything. He's just going to do this, this simplistic math based on what's in the textbook, and it's not going to be proving a damn thing.
Energy is defined as the...
It's not going to prove there's 4 times the heat in the ground. It's not going to disprove that there's 2 units of heat in the ground. It's not going to do any of that. It's just going to make a claim with no evidence. And with a substantial piece of evidence against it. And the substantial piece of evidence against it is his own drawing. This is what 1 velocity looks like. This is what 2 velocity looks like. We know the 1 velocity has to happen at some point. At some point, the thing going 2 velocity has to go 1 velocity. We already know what that looks like. It's this little tiny thing over here, this 1/4 of the experiment. We know this 3/4, okay, is where half the energy, half the velocity was lost over 3 times the distance. Well, why is that? Well, because it was going faster, and per inch it weighed less. Obviously. Absolute fact. It just plainly weighed less per inch. It pushed into the surface less per inch. Absolute fact.
Ability to do work. Work is defined as essentially this equation, the amount of force you are pushing with in the direction the thing is moving, and multiply.
All right, I'll cut you a break, and I'll play it and see if he says anything relevant. All right, this might be relevant.
That change. And that will give us the amount of force. Based on the amount of force and the distance the object moved,
there we go.
We are observing this quantity that we call work.
All right, so he's saying the distance is work. And obviously in the circumstance, it's clearly not, because there's no proportionality to the work being done. You go this much distance with 1 velocity, and you go this much distance with the other half of your 2 velocity. So that lack of proportionality he's not dealing with. He's claiming the friction is constant. And clearly the fact that you can slide over thin ice proves the friction isn't constant. The weight isn't constant. Your pressure on a surface is not constant regardless of your velocity. The faster you go across the surface, the less per inch you weigh, the less you per inch apply pressure. That's the argument he has to get to, and I bet he'll never get to it in this video. So I'll pause and see what happens. Well, this was a rather stunning pile of crap. I'm not talking about the real universe. I'm not talking about how things really are. I'm not talking about what heat is. I'm not talking about he's not talking about anything that has to do with the actual physics. Heat is what all energy converts to. If it doesn't convert into some piece of matter's linear motion, it always leaves the experiment as heat. It's one of the most substantially meaningful things in understanding the cycling of energy in the universe, is understanding heat. Thermodynamics is really physics all over the place.
What the number is, so we can write that number down, and we are making no claims that there are relationships beyond the definitions. Nothing about what happens in the world.
Right. So he's basically saying, look, I just think distance is energy, and that's it. And so I don't care whether the friction changes. I don't care whether more work was done on the ground. I don't care whether more heat was made. Because I just believe in my Holy Ghost, and I just do the Holy Ghost math. So this isn't science. This is just rubbish. I don't have to be obedient to experimental proof. I don't have to in any way logically defend what I'm saying, because I don't have to deal with anything that's real. Heat is real. It has to be accounted for. You can't make heat for free.
I have made no claim of how energy is related to heat. I have made no claim.
But that's the whole point. The whole argument is obviously it has to be related. That's why we have the thing called a joule, is because Joule proved basically that, yeah, you can just convert anything into this simple, smallest amount of, the simplest form of energy. And then you can know how much energy it actually had. You can measure its energy by converting it all into heat.
About how energy...
And that's what rolling does. It converts all of the linear motion substantially, with tiny bit of air resistance, tiny other little things, and it converts it into a heated ground.
Is related to electrical power or anything of that nature. I'm working only from the definition that energy is work. And I'm doing that so that...
And work is distance. So that's it. He's just telling us what their Bible says, and he's not going to give us any indication that anything in that Bible is true. So there's no evidence that kinetic energy does work, okay? I mean, a ton of experiments show it doesn't do any work. So, so what's the point of associating it with the doing work when it doesn't, when it fails to do work all over the place? And where your whole argument is it made heat, So in the ballistic pendulum, he's going to claim, oh, there's a whole bunch of heat in the pendulum. That's where all the kinetic energy is. He's going to claim it's there. How come he thinks heat is irrelevant in this experiment? How could it possibly be irrelevant in this experiment, somehow relevant in the other experiment? I mean, this is just such a evasive crap. Oh, geez, ask a simple question, get absolute, verbal, diarrhea as an answer. All right, so right here he's going to give away that he thinks friction is constant. So even for the one mass, it's doing the same thing. It's traveling right here, half its speed. It's doing the same thing. It traveled 3 units of distance, and it lost half of its speed in this last quarter of the distance. So again, the velocity wasn't anything like constant. The deceleration wasn't anything like constant. So this is, again, just more of their bullshit. They tell you something, but they don't show you something, and they definitely don't prove anything. And so this goes all the way back to Galileo. Galileo already established how gravity works. 1, 3, 5, 7, 9. It's not constant.
Tripped up about this square there. Just like it's written here, that just means meters per second every second. So for every second it was sliding, it lost 0.5 meters.
Right, so it didn't. That's just an absolutely provable fact. That's not what happened, because it didn't happen here. So we know with the 2 mass, we know it's going 1 velocity here because this experiment will be identical to this experiment. So we already know it's going 1v right here. Okay, 3/4 of the way down the track, it's going 1v. Well, I guess it would be right here to use the front of it. That's where it's going half its velocity. So he's saying it's going half its velocity halfway down the track. No, it's not. You got it wrong. That's not where it's going half the velocity. So you're just factually wrong. It's not 0.5 meters per second, and it certainly isn't any seconds squared nonsense. It's not 60 miles an hour squared. You don't go 60 miles an hour squared down the road.
Meters per second. That's what this says here. And it was sliding for 2 seconds. So in the first second, it lost 0.5.
No, it didn't. So that's an absolutely provable fact. So that statement is absolutely wrong. We know it from the 2 velocity experiment. We know it's not going half its speed at half the time. Half the time is right here. Okay, that's half the time is right here. 1 second to get here. The second to do this little tiny distance. That's the absolute fact. So again, you just cheated the truth dramatically to make your silly argument. To defend physics you've never tested. You've never been interested enough to test it.
In the second, it lost another 0.5. And so it took 2 seconds to run out of speed.
Didn't happen that way. False. Phony, fake, fraud. You're absolutely wrong. You're teaching crap because that didn't happen. And it's a logical proof. You can't evade the logical proof because it's right here in your second experiment.
Right? That's what that says right there. Let's do the yellow one. Yellow one starts at 2 meters per second, and it slides for 4 seconds. So let's plug that in. 2 meters per second divided by 4 seconds is also 0.5 meters per second squared. Meaning, the yellow object is losing half a meter per second for every second that it slides.
So silly, right? We know that this whole thing is 1 second. So yeah, it's a gigantic amount of distance. So you can't make the same argument that it's related to half the distance, half the velocity. It's just not true. And this one demonstrates it's not true.
So this is half a meter per second for every second. That's what that notation indicates. And it was sliding for 4 seconds. So in 4 seconds, we've used up all of our 2 meters per second.
Okay, so maybe he misspoke. We know it didn't slide for 4 seconds. So why'd you put 4 seconds here? You know, that's just a stupid mistake, I guess. Oh, it's twice the seconds. I'm sorry. But we know it didn't lose. It didn't go 0.5 here. It didn't lose 0.5 here, 0.5 here, 0.5 here, and 0.5 here to add up to the total of 2. So he just should have used 1 and 2 as the velocities, and this wouldn't be a mess. Yeah. Because then you'd have 1 second and 2 seconds instead of 2 seconds and 4 seconds. But anyway, so that's what he's saying. He's overtly saying in this 2 units of distance, it's now lost 0.5. And then in this 2 units of distance, it's going to lose 0.5. And then in this 2 units, it's going to lose 0.5. Because if you take that as the conclusion, it doesn't explain the last part being only 1 second. That's 1 whole second, and you lost 15. You lost 1.5 in 1 second. You didn't lose 0.5 per second. Okay, I don't know if I said that right.
Okay, there's our accelerations. The acceleration together with the mass allows me to get the force. And I've written here force of friction. We're presuming that
we know it has half its velocity 3/4 of the way down the track. So again, it can't happen in half the distance.
The reason that the objects stopped sliding was that they were experiencing friction with the sliding surface. It's a thought experiment, so we are discounting any other source of potential force. I'm calling it friction, and we're presuming that it's a constant rate. Really, what we've observed here is just the average force acting on the object as it was sliding over the period of time that it was sliding. We can't actually say for sure with the data that we have. We can't say that all...
Pause the wrong thing. Yeah, so I'll pause the video. I mean, it's not doing anything. He's just going to do the F equals ma. He's not going to concede that the friction changes, so there's really no argument here. He says it's 4 times the energy because it's 4 times the distance. Obviously, I'm saying there's not 4 times the heat in that ground, because obviously you only applied 2 units of weight, 2 units of pressure, 2 units of force pushing the object into the surface that's going to take the energy away. And again, the thin ice, sliding over thin ice, proves the argument. Clearly, you can change how much you weigh by moving quickly across a surface.
Observed that it moved 1 meter. So that's 1/2 of a Newton meter. A Newton meter is also called a joule. Usually you stick with Newton meters. It's not that much of a mouthful, but you could call that a joule if you want. The yellow one was also experiencing 1/2 a Newton, but we measured it move 4 meters. So multiply those out, we got 2 Newton meters. What is the point of all this? Energy was defined to be the capacity to do work. Work was defined by this equation. We worked it out.
Okay, so there's just no point, right? He's just saying because it went more distance, it did more work. And the simple truth is it didn't. Because the simple truth is it's just like dropping something and I apply a constant force pushing it into a surface. Any idiot could understand that the faster it goes through paint spray or some kind of mechanism pushing, the faster it goes through, the less that force hits it, the less, like say, ball bearings or sandblaster. Use a sandblaster, and we're going to push an object into a surface to slow it down. Obviously, the faster it's going, the less sand it's going to hit it in a period of distance. And it's going to apply less force into the surface, and it's therefore going to slow it down less. So that's the simple argument he's completely ignoring. The friction isn't constant.
Quantified it. The numbers say the amount of work for the yellow object was 4 times the amount of work of the blue object.
So there's no evidence it did 4 times the work. There's no evidence there's 4 times the heat in the ground with the 2 velocity object. There's no evidence that 4 times the weight was put on top of it. There's no evidence that you could possibly create 4 times the heat in the ground. So again, there's just no point, in saying, well, I'm just doing a thought experiment because our physics for 350 years couldn't bother doing any of these experiments. Couldn't be bothered proving anything. We just preach. We don't prove. That should be their motto. That should be the motto of physics. We just preach, we don't prove.
And this was your question. Explain how it is that it has 4 times of energy. Well, honestly, the reason it has 4 times the energy is because that is how energy is defined.
So, yeah, it's just ridiculous. It's defined, work has a real specific definition. Work isn't just traveling a distance. Again, you have to explain how, well, where is it? What's it doing now? It's going somewhere. You're saying 4 times the heat is now in the universe somewhere. Well, what's it doing right now? You didn't use 4 times the work to compress the spring twice as much. So how does this equation make any sense? I didn't use 4 times the work. I didn't compress the spring 4 times to get twice the velocity. I'm going to compress it twice as much, and it only takes twice the work to compress it twice as much. That's Hooke's law. So where is your example? You start with 2 units of work that you did, and now you have 4 units of work out. Isn't that free work? By your definition, by your mathematical formulation? Do you really think if I crash the block into another spring, without letting it have any friction at all, just in air, that it's going to compress the spring 4 times as much? No.
We measured that they have the same mass, 1 kilogram. We measured their starting velocities at 1 meter per second and 2 meter per second. Energy is the ability to do work. So
Okay, so I don't know what he does for the next 10 minutes. Do you really want to pay attention? Well, let's look. I'm going to have to endure it, so you might as well have to endure it also. What's he going to say for the next 10 minutes? I mean, he's ignored the subject, which was, do you have any evidence that 4 times the heat is in the ground? That's where all the energy is now. It's supposed to be in the ground. The object stopped moving. All of the energy's out of the object, so where is it? And do you have any experimental evidence that there's 4 times of it? That there's 4 times the work was done on the ground? That's where the energy is, so obviously that's the place you did the work.
we need to apply the equation for work. We did those equations, worked through them, and quantified how much work that is. It's half a Newton meter for the blue object, and it's 2 Newton meters for the yellow object. That is a ratio of 4 to 1. And so why is that? It's because that's the definition of energy in physics class. I believe that you're trying to say, what is this 4 times energy good for? Can I do work? Is work useful? Can I do something to show that I get 4 times the result in some way other than just this math? The math says I can do 4 times the work, whatever work is. But what does it mean to me, like in a practical sense, right? I think that's what you're trying to get to.
I don't think that's exactly what he's trying to get to. Is just, do you have any evidence at all that it actually, there's 4 times the amount of joules of energy in the universe somewhere that went through this experiment? This experiment, there was 4 joules, you're saying, or whatever the number is. Show me. Show me where it is. The 4 units.
It seems kind of unintuitive that starting the block with twice as much velocity would have 4 times the much of something meaningful. But let me put it to you this way. What is...
All right, so again, this is all in the context of me saying, how many fucking times in the last 10 years have I said 25 times the fuel to go 5 times as fast? We know this gets even worse. It's not about this 2 to 1, this 1 to 4 thing. It's about the 1 to 9 thing. Well, 3 to 9. And then it's about the 4 to 16 thing. And then it's the 5 to 25 thing. It just goes all kinds of south.
Something meaningful. What does that even mean? We have this definition for work, and we could discuss and debate whether this form of work is meaningful. But you said yourself the object moves 4 times the distance. Is that not meaningful? It seems like there's a point of view, at least, where this 4 times distance was useful. If my work is to move the blocks, right? That's my whole job, and that's the work I'm trying to do, is to move these blocks.
Again, this is all in the context. We already know all the science for meteors crashing into the Earth. They don't gain anything hardly from our gravity. It's just a fact, because they're going so much faster than the gravitational force would even add anything to their speed, because they're going through the gravity so quickly. So again, it's a time-dependent force. It's clearly time-dependent. It's in units of time. It's not in units of distance. And you're just claiming for some dopey reason that as you change the friction, you do the same amount of work. And you don't do the same amount of work when you change the friction. You don't heat the ground as much when there's not the same amount of friction.
You try to move the blocks, you give it 1 meter per second, and it moves 1 meter distance. If I give it 2 meters per second, only twice as much speed, I got 4 times of my work done, if that is my work, right? So I think what we'll want to do, and what I want to do with this is come to an...
So it would be even better if you would say well, look, I have 3 times the velocity, and now I can do 9 times the work. Yeah, just 3 times the velocity, 3 times the spring compression, and I can do 9 times the work. I can't show you an experiment where that happens because, frankly, it doesn't happen anywhere in the universe. But I'll say it happens. And that's all you're doing. You're just saying so. You have to show so somewhere.
Understanding with the vocabulary, and then try to have meaningful discussions about what is useful about this thing we call work, if anything. It could be that it's just a silly mathematical thing that we're just using. Okay?
The meaningful discussion would be about your evidence. And so far, all you've cited is the worst trolls on the internet as sources of evidence. A huge bias, let's just say. People with a gigantic chip on their shoulder. Okay. They're not honest seekers of the truth.
All right, so here was the next part of that same first question. It says KE versus MV. Momentum is really energy, while kinetic energy isn't. That's the crucial point.
KE versus MV. Momentum is really energy, while kinetic energy isn't. That's the critical point. Okay. I don't know why he wrote that instead of just showed it, but whatever. Obviously, the critical argument being made is that momentum is what Descartes, Galileo, and Newton understood to be energy. They never had any idea that there was any v squared notions, and they won the argument decisively, and it wasn't until Leibniz was long dead that this crappy theory was resurrected for no good reason. Not because momentum didn't work. Momentum worked just fine. It wasn't because momentum was broken. It's because physicists were gullible and stupid, frankly.
We have definitions for energy using work. We do not have a definition yet for momentum. Here is the definition of momentum, and you stated it right there in your question, so I know you know what it is. It is defined as the product of an object's mass and velocity. That's couldn't be simpler, it's just mass.
Yeah, couldn't be simpler. Obviously, that has a consequence in the universe. It exchanges its momentum with other objects. So it's just ridiculous to pretend momentum isn't exchanged. Of course it is. And when it's exchanged, you call that exchange doing work. This is so pathetic.
Mass times velocity, and we'll write it with a P. P for momentum. This episode is brought to you by the letter P. So P for momentum is just the mass times the velocity. And we'll just put...
So it's not surprising he's using Sesame Street jokes.
That's in our table of vocabulary. You knew this one, but we'll just put it on there for completion. And I want to put it on there for comparison, because you had said that kinetic energy is momentum. And I'm saying, well, it doesn't look like it. At first glance here, I have very different sounding descriptions of these two things, and the equations that I'm given make it pretty clear what exactly we're trying to get here. And they don't look the same. So
I don't understand. Where did you ever see kinetic energy? I've never seen it. I've seen momentum. I've seen masses moving velocities. Where did you see this scalar energy anywhere? Please show me. Show me the experiment that shows the scalar energy. Where I can see it doing something. Scaling. Show me scalar energy.
Reminding you, the definitions that we got from Bijou's. So this is a typical contemporary physics high school classroom definition.
And that's meaningless, because it's just talk. No evidence, just talk.
And I'll say it again, this is nothing in these three statements is making a claim about how the universe works. It's not making a claim that...
what's the point of talking then? What are you talking about? The science isn't about reality, it's about mathematics. And it's not even mathematics coherent to reality. It has to be coherent to reality. There's no point in having the discussion if we're not going to have a discussion about how does the real world work. Not how is it your Holy Ghost, what kind of necktie he wears. I don't care what kind of necktie the Holy Ghost wears.
Work is useful as a quantity. This just
more mush talk. That wasn't the definition, but whatever.
Is telling us what that quantity is. So ideally there would be no skepticism about these definitions. If you want to look in other texts to find alternate definitions, I'm open to that. We could find alternate definitions. They'll be close to this if we're looking at a contemporary high school level text.
Yeah, right. If we look at Newton's definition of quantity of motion, it's mass and velocity. Yeah.
So let's look at the momentum then. Let's investigate the momentum question and compare that to the energy
Not velocity squared.
that we have already calculated. So here we are. Momentum is just mass times velocity. Let's fling our guys. The first one,
I mean, saying it's just mass times velocity is ignoring the fact that it travels distances and it does work. So, I mean, it's just silly to say momentum is just a velocity that doesn't go anywhere. Yeah, it does go somewhere, and it does have contact with things, and it does exchange its MV. And in all the experiments, it only exchanges the MV. It doesn't exchange the kinetic energy.
blue one has 1 kilogram of mass. It starts at 1 meter per second. So that's 1 kilogram meter per second.
All right, so there's no, he's just going on the same shit again. All right, so obviously, look, what we want is a reaction to the accusation that the amount of friction is changing with velocity. They're presuming the friction is identical regardless of velocity. Obviously, that's the experimental argument. That if the friction is less, the object is losing less energy per inch. That's the absolute facts. The factual assertion.
And using that same relationship I said earlier, where a kilogram meter per second squared is a Newton, that means a kilogram meter per second is a Newton second. So I'm going to use this little shorty hand, Newton seconds, for the units of momentum. Our blue object launched.
Why? Why bother? Just use one unit. Just say, put it all in joules and just convert your newtons into, 10 newtons equals a joule. Why play all this crappy game?
Is with 1 Newton second of momentum, and then as it slides, it's losing its momentum. It's giving its momentum to the sliding surface, and it's giving it away. It's losing its momentum as it goes, and it eventually comes to a stop.
Yeah, clearly the one block has 1 unit of momentum. The second block has 2 units of momentum. You're squaring the velocity, so you're saying it's 4 units of energy when no, it's not. So we're just talking about this arbitrary square that you've placed on the momentum that completely perverts and exaggerates and breaks any continuity that could exist in the universe. You just broke something that worked perfectly well for no good reason. What was the good reason? Why don't you tell me why, in the 1700s, science switched sides and decided they had to have kinetic energy? What defect did the theory of momentum have that need to be fixed?
The yellow object starts with 2 meters per second, so it's got 2 kilogram meters per second of momentum, or 2 Newton seconds of momentum. It has twice as much momentum, and the floor is scraping that away at the same rate. So it takes twice as long for all that momentum to go.
So he just said it as clearly as he could say it. The force is scraping that energy away at the same rate. We know it's not the same rate. We know it's going half its velocity here, 3/4 of the way down the track. So again, it's just bullshit to say it. It's not, the friction isn't the same per inch. It's constantly changing. As the object slows down, the friction's getting more and more onerous. It's sucking more and more energy out of the object per inch the slower it goes. Absolute fact. You ignored it entirely. Blah, 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 blah.
Go away. Cool. Let's summarize in a big old table here. Here's all the data that we looked at for these 2 examples in our thought experiment. We have the same mass for both shots. We have twice the velocity, 2 times the velocity.
And nowhere was any joule measured. So no joules of energy were measured in any surface or anywhere. It was the collected energy wasn't measured. The energy extracted wasn't measured. None of that happened.
And that led to the object sliding twice as long, took twice as long to come to a stop. But it managed to cover 4 times the distance in that period of time. The accelerations we observed during that time was the same. It's just that the acceleration acted over a longer period of time in this case, right? So the acceleration...
So the deceleration wasn't the same time. It decelerated half its velocity, got taken away over 3 units of distance, and then the other half over just 1 unit of distance. Fact.
and
Perfectly consistent with Newton's gravitational law. I mean, Galileo's.
thus the force we observed was the same during that period of time. But here's really the question. The work and the momentum. The work and the momentum are right here. The doubling the speed of the object doubled its momentum. But doubling the speed of the object seems to have quadrupled the amount of work that we did.
And what did you do work on? So again, he keeps pretending the work is in the distance, but that would be magic. What was the work that was done? The work done was the friction, the force put into the ground. The vibration of the ground is where the work went. And did you measure any of that vibration in the ground? Of course you didn't.
And why is that? Because of the way work is defined, right? I say it a million times here. I'm not trying to claim that work is conserved, that any kind of relationship to anything in the real world outside this number has any meaning at this time. I just want to agree that
I don't even know why he bothers with this. Again, it just diminishes the whole conversation. If you're not talking about reality, then just leave me alone. Go somewhere else and don't pretend to be a scientist, because scientists are supposed to be talking about reality.
we did observe 4 times the work by
I didn't
applying
observe 4 times
twice
the work.
the momentum to the object. And that should immediately trigger you to be perhaps puzzled. It doesn't seem immediately intuitive, but let's look back up on the chart here just a moment and see that it took the object.
So again, there's no point. 3 times the velocity is 9 times the work. 4 times the velocity is 16 times the work. Bullshit. You have nothing, not even any experiment anywhere close to demonstrating that kind of crap. Nothing. Even close.
It took twice as long. This is the time column. It took twice as long to come to a stop because it had twice the momentum. But it traveled 4 times the distance. Thus, we said it did 4 times the work. This is the exact relationship that we're looking at.
And again, the simple argument is it only traveled 4 times the distance because there was less friction for 3/4 of the trip. 3/4 of the trip, it was losing less energy per inch. Absolute fact.
Relationship between momentum and force. Here's the force scalar. This is time. Momentum is a force acting for some period of time. So if we doubled the time, we doubled the momentum. Energy, though, energy is in units of Newton's meters. So it's a force acting over a distance. So if we could quadruple the distance, we quadrupled the work. That is how it goes. And if you don't like this, saying, oh, I don't like this work unit, you still have this distance unit. That was something you gave me in your original problem.
So there really isn't no point, right, to talk to these people, because you have to preface your argument with, I only want evidence that it's 4 times the energy is in the ground, because that's where you're pulling it into. The ground is sucking the energy away from the objects, and the argument is, can you prove there's 4 times the energy in the ground? That's all that we need to hear you say is, no, you can't prove it. So you're just saying so. And that's all you're doing. You're making a claim with no evidence. And obviously, at least I have the piece of evidence on my side, which indicates that the friction clearly isn't even. And I can prove it with thin ice, and it can be proven by understanding that it went 3 times the distance and only lost half its velocity.
Original formulation of the problem, you had the distance was 4 times as much. If we're making up our own definition of what does it mean to do work, I think it would be reasonable to imagine we could suggest that the amount of distance we moved an object is relevant to how much work we did.
All right, so again, it's just kind of silly because you're not counting what did the work. If I just shoot 2 things in space, twice the velocity is only twice the distance, right? Because nothing is taking the energy away. The whole point of talking about rolling or friction or pushing or sliding is to create an experiment that collects the energy.
In the situation, right? If you moved your object 1 unit and I moved my object 4 units, did I do 4 times the practical work? I think that's a discussion we can have now.
I don't, again, there's no discussion because there's no evidence. You don't have any evidence, so just say that you do physics, you make claims, and you don't have to prove them. You can just say it's v squared, and you don't have to show me anywhere. You don't have to show me what scalar energy looks like. You don't even have to draw me a picture of scalar energy. You just say it's there somewhere. It's magic. And then you'll never stick a thermometer anywhere to measure the heat you claim is in places that it ain't. And then you won't measure it because you're saying, I don't care what the heat in the surface is. Well, that's the whole experiment. All the energy is in the surface. Most of it. Obviously, if it's a sliding block, you put half of the energy into the sliding block in terms of heat.
But for now, I just want to stress that these are just numbers, and they are just quantities that we have defined to be this way. And so if it puzzles you that an object can do 4 times the work when it's only twice the momentum, I'll say that is because of the way we define the word work.
It doesn't matter. The fact is, show me an experiment where it does work. Show me where it works. Show me the work doing work. Show me work working, work. Show me work happening and your proportion. Show me 5 times the fuel creating 25 times the work. Show me.
Work and momentum have specific definitions, and they're just not the same definitions. And at this point, it's been 30 minutes already, so let's stick a pin in this one. We'll come back with a part 2. The call to action, dear viewer, the follow-up for this part 1 video is to acknowledge or discuss the definitions that I demonstrated and whether my quantities do match that definition. Let's launch off from this video, and if we agree to the vocabulary, we can then start the conversation about
why would anybody agree to this crappy vocabulary? Work is distance. It's obviously not distance. Sliding on ice proves it. Lots of different ways you can prove, you can change how much work you're going to do and how much distance you're going to travel. I change the friction. I dramatically change how much the thing is going to keep moving. So, how much, it's just such an obvious statement. I change the friction. I change how much energy I take out of the object. Duh. All right. So this, the part 2, I won't do this again. So I guess I'll have to play the video first and then try to find some clip in it that's worth playing. But, this was just a waste of time. So sorry about that. It's an hour of, I could have just said, maybe I'll do another video in the beginning of this video and just tell you don't bother watching the video because he's not going to talk about any of the subjects that matter. Yeah, I'll do you that favor.